Let's work some example problems regarding complex power and power factor correction and all that kind of stuff. So all I've done is just brought a random circuit analysis textbook out of my office. So just grabbed one of the 7 that I have, and we're just going to work through some problems and see what shakes out. Okay. So the first circuit that I wanted to look at is this guy right here, where we have some time varying voltage source Vs of t, and I'll define that in a moment, connected to a 30 ohm resistance, which is in turn connected to a 40 microfarad capacitance. We have a 60 millihenry inductance here, and I'm going to call this current Ix of t. Over here, we have a 20 ohm resistance. And then here we have a current controlled voltage source. And let's specify what our goals in this problem. Wait, actually, hold on, let's say that Vs of t is 100 cosine 2000 t volts. And we want to find the power factor at which our independent source operates. So I'm going to put PF independent. I'm going to put here we're going to be looking at supplied power, and let's do PF dependent for our dependent source. And for this one in particular, and I hope this doesn't wind up biting me in the butt, but worst case scenario, we're just going to wind up with a negative power factor. I'm going to do the dependent source as the supply. Okay. So how we are going to determine those two power factors is by first determining the complex power supplied by our voltage source. So let's call that S independent, as well as the complex power absorbed by our dependent source, S dependent. And in order to calculate those two complex powers, we need to be analyzing this circuit in the RMS phasor domain. Okay. So we're going to convert our circuit out of the time domain into the RMS phasor domain. So what should my source voltage look like in the RMS phasor domain? So what would it look like as just a phasor? Let's start there. 100 angle 0 volts. So to convert that to an RMS phasor, we just divide the magnitude by square root of 2. So it'll be 100 over square root of 2 angle 0 degrees. Doesn't have to be any harder than that, right? So 100 over root 2 angle 0 degrees volts RMS. So we've got our voltage source taken care of. Our 30 ohm resistor is going to continue to look like a 30 ohm resistor. We'll take care of our capacitor and inductor in a moment. 20 ohm resistor is going to continue looking like a 20 ohm resistor. And then this is going to, sorry, this is a voltage source, is going to look like 4 IX, where IX is now being represented by an RMS phasor signal. So let's Go ahead and draw that in our circuit diagram here. All right, so the impedance of our capacitor. What's the impedance of a capacitor in general? Capacitor. Negative J over omega C. All right, so negative 1I over, so what's omega here? 2000 radians per second. C is 40 micro, so that's 40 times 10 to the minus 6. So this comes out to be negative J 12.5 ohms. For our inductor, we have an impedance of J omega L. So that's going to be 1I times 2000 times 60 times 10 to the minus 3. And that comes out to be J 120 ohms. All right, so let's sort some things out here really quickly, okay? So in order for us to find the complex power that is being supplied by our independent voltage source, we are going to need to figure out what this current is. I'm going to call this current I independent, like so. And in order to find the complex power absorbed by our dependent source, we need to be able to figure out what the RMS phasor current flowing into the positive polarity terminal is. So I'm going to call this I dependent, like so. So there are a multitude of different ways that we could potentially solve this circuit for those two quantities. I want to hear what your thoughts are, since we haven't worked very many frequency domain example problems as to this point. And then if it's not the way that I would do it, then I will tell you how I would do it. So how would you guys think you could solve this? So we definitely could do mesh analysis. However, mesh analysis will require the use of a computer, because I am far too lazy to do Cramer's rule or substitution in order to solve that system of equations. So it's definitely a possibility, but it is not a possibility that we can easily do without the aid of a computer. So I don't disagree with that as a thing. That being said, on at least the take home, or excuse me, the in-class portion of your test, mesh is effectively not an option. So let's think of something else. All right. Well, since you guys are not volunteering anything else, I am going to talk about how I would solve this thing. So when I see a circuit like this, what I typically do is I'm going to call it a modified nodal analysis, but realistically, it's just applying Kirchhoff's current law and a little bit of algebra in order to sort things out here. So I use this method whenever I have only one unknown voltage in the system. So I'm going to redraw my circuit very slightly, okay? So over here on the left, I'm still going to have my voltage source. So 100 over √2 angle 0 degrees volts RMS. And I'm going to lump that resistor and capacitor together as a single impedance. So this is going to look like a total impedance of 30 minus J 12.5 ohms. So the reason why I did that is because those two impedances are just in series. And so I've effectively eliminated a node if I were to do nodal analysis or something like that. Now I have my J 120 ohm impedance here. my 20 ohm impedance here. And here is 4 IX. Here is IX. Like so. Okay. So what I'm going to do is I'm just arbitrarily here choosing this bottommost node to be my reference. And I am going to solve for this nodal voltage Vx. So if we look at what we're looking for here, this current I independent is going to be nothing more than our source voltage minus whatever we find Vx to be, divided by that impedance of 30 minus J 12.5. So finding that voltage Vx allows us to find that current very easily. This current I dependent would simply be Vx minus the voltage at our dependent source divided by 20 ohms. So once again, if we can figure out what that nodal voltage Vx is, we can get those two currents that we need very, very easily. So I'm choosing to solve for Vx as an intermediate step because it allows me to solve for everything else I'm interested in with just a little bit more math, okay? So I'm just going to apply Kirchhoff's current law at this node, okay? So I would have Vx minus 100 over root 2 angle 0 degrees volts RMS divided by 30 minus J 12.5 ohms plus Vx over J 120 ohms plus Vx minus 4 Ix divided by, excuse me, that shouldn't be a J there, just 20 ohms. Okay. Is equal to 0. So right now I have one equation and two unknowns, so this is still looking a little gross. But we can just use Ohm's law to figure out what Ix is, right? So using Ohm's law, and I'll do that up here, we would just have Ix is simply Vx divided by J 120 ohms. And so anywhere we see Ix, we can simply substitute that in, right? So that's going to look like Vx minus 100 over root 2 angle 0 degrees volts RMS divided by 30 minus J 12.5 ohms plus Vx over J 120 . So I'm going to do something might seem a little bit odd here, but I know that Ix is Vx over J 120. So I'm going to do J 120 ohms over J 120 ohms Vx minus 4 Vx over J 120 ohms divided by my 20 ohms here. So the whole point of that, so I'm going to set this equal to 0, is that now I can lump this together, right? So I have effectively in the numerator a J 120 minus 4 times Vx, and I can just take this 120 and multiply it by this 20 down here. So let me move some things around now, right? So let's look at what I'm going to have here. Okay, so I'm factoring out a common factor of Vx, and all of my Vx terms are going to be on the left-hand side of my equal sign. So the first thing that I see is a factor of 1 over 30 minus j 12.5 ohms. Then I'll have plus 1 over j 120 ohms. And now I'm going to have j 120 minus 4 divided by j 120 divided by 20. And that will be equal to 100 over root 2 angle 0 degrees volts RMS. All of that divided by 30 minus j 12.5. So anybody see anything too weird or wild with my algebra here? All of the steps that I've taken make sense and I appear to have performed the algebra correctly? Okay, so this big thing right here is literally just a number that we can put in our calculator. So I'm gonna put this in my calculator and store it as A, and then I'm gonna put this in my calculator and store it as B. So I'm gonna do the A bit first. So 1 over 30 minus 12.5i plus 1 over 120i plus 120i minus 4 over 120i over 20. And I get this part right here to be 0.0786 and some change with an angle of 3.771 degrees. The units on this should be per ohm. Storing that in my calculator as A. On the other side, I have 100 over root 2 angle 0 divided by 30 minus 12.5 j. That comes out to be 2.176 with an angle of 22.6198. So let's call it 620 degrees. And that has units of amps. Store that as B. And now we can find Vx to be simply what I have stored in my calculator is B divided by what I have stored in my calculator is A. And so that comes out to be 27.691 with an angle of 18.849 degrees volts RMS. I'm storing this in my calculator as X. And now I can say that I independent is just my source voltage, 100 over root 2, angle 0 degrees, volts RMS, minus Vx divided by 30 minus J 12.5 ohms. So 100 over root 2 minus what I have stored as x divided by 30 minus 12.5 J comes out to be 1.397 and some change with an angle of positive 11.254 degrees. Amps RMS. Storing this as Y for when I use it in a moment. And I dependent is Vx minus 4 Vx over J 120, all divided by 20. And putting that into my calculator, let's see, x minus 4 over 120 I times x all over 20, 1.385 with an angle of 20.758 degrees amps RMS. I'll store this as Z. All right, so recall please that our power factor in general is simply the cosine of theta V minus theta I. So the power factor for our independent source is going to be the cosine. So theta V here is the phase angle of the voltage drop across our independent source, which is 0 degrees, right? And then we're going to subtract from this the cosine of our current, the phase angle of the current flowing through the independent source, which is 11.254 degrees. So cosine of negative polar angle of what I have stored as y, and I get 0.98077, so let's call that 1. Should this power factor be leading or lagging? So is 0 minus 11.254 a positive number or a negative number? It's a negative number, and since the angle is negative, we have a leading power factor. Okay. Now, let's do the dependent source, right? So same expression. So now our phase angle is for our voltage, or excuse me, theta V is the phase angle of the voltage drop across our dependent source. So our dependent source has a value of 4 Ix. So 4 is just a constant. So whatever the phase angle of Ix is going to be fine. Well, that's just going to be Vx divided by J 120 degrees. So that's just going to be whatever Vx is minus 90 degrees, or the phase angle of Vx minus 90 degrees. Just for shits and giggles here, actually, let's just go ahead and do this. So x over 120 I is going to be 0.231 with an angle of negative 71.151 degrees, amps RMS. So just to be really quick here, notice that Vx was 18.849. If we subtracted 90 from that, we would get this exact number, exactly like I said it would shake out. Okay. So we're going to have negative 71.151 degrees minus the phase angle of our current, which in this case is I dependent. So that would be 20.758 degrees. So let's see, that's the cosine of polar angle of what I just stored as t minus polar angle of what I have stored as z. Oops. And I get negative 0.033. So the negative sign here, all it means is that this source is actually also supplying power. So we did all of our calculations for absorbed power because we got a negative power factor. That literally just means it's actually supplying power. Okay. Negative 0.33, so is negative 71.151 degrees minus 20.758. Is that positive angle or a negative angle? Very obviously a negative angle, right? So this is also going to be at a leading power factor. If we had chosen to do the dependent source as supplied power, this would actually look like positive 0.033 lagging. So the phase angle of the current would be 180 degrees out of phase. So we would have been finding I depth flowing up. So if we were to add -180 degrees to this, that would look like minus 200.758, right? So let's throw that in really quickly. Cosine negative 71.151 minus 200.758 comes out to be positive 0.333, blah, blah, blah. Well, negative 71.151 minus 200.758 is negative 271. We add 360 to that to get an equivalent angle. It's 88.091 degrees, which is why I would say that it would be a lagging power factor, because I want the magnitude of my angle to be as small as possible. So anything more negative than 180 degrees, I would add 362 to make it show up as a positive angle. So. And seeing that angle come out to be 88.091 kind of explains why this power factor is so incredibly small, because we know that at 90 degrees, plus or minus, it should be exactly 0. All right, so we did some things there. Let's find something else to do. All right, so here's our second example. Let's say that we have a 50 angle 50 degrees volts RMS voltage source connected to 2 ohm resistor. And then I'm going to have an impedance here. Let's call it ZX, and I'll define what it is in a moment. And let's put an impedance over here, and let's call it ZY. So let's say that ZX is 10 minus J5 ohms, and ZY is equal to 8 plus J6 ohms. And I want us to determine the average power absorbed by impedance ZX, the reactive power absorbed by impedance ZY, and the total complex power supplied by our voltage source. So in order for us to find the total complex power supplied by our voltage source, we are going to need to know the current that's flowing into the negative polarity terminal of our voltage source. So I'm going to call this IVS, and it has this particular direction. So that's one thing that we're definitely going to have to figure out in the process of solving this problem, okay? In order to determine the complex power absorbed by impedance ZX, we would need to know some combination of the voltage drop across impedance ZX or the current flowing through the impedance ZX. And similarly, in order to find the complex power associated with impedance ZY, we would need to know either the voltage drop across ZY or the current flowing through ZY, right? So if we know both, we can calculate the complex power, but we also have those alternative relationships that we developed in our last class meeting to where we only need to know the voltage or we only need to know the current. So I would argue here that solving for the voltage Vx is the best thing to do, because the voltage Vx and the voltage Vy are literally the same voltages, because impedance Zx and impedance Zy are in parallel. So if we can solve for that voltage Vx, that's going to allow us to calculate the complex power absorbed by impedance Zx, as well as the complex power absorbed by impedance Zy. And then we can just use effectively Ohm's law. So 50 angle 50 minus Vx over 2 ohms to give us the current that's flowing through our voltage source. So that one piece of information allows us to do everything else within 1 to 2 steps. So how do you guys suggest we should solve for the voltage Vx? Absolutely, that seems like the easiest thing to me as well. So we can say that our voltage Vx is going to be 50 angle 50 degrees volts RMS times Zx in parallel with Zy divided by 2 ohms plus Zx in parallel with Zy. So that's going to look like 50 angle 50. Actually, I'm going to do Zx in parallel with Zy. Save that in my calculator so I can be as lazy as possible, because that's what I'm all about, right? So 10 minus 5i times 8 plus 6i divided by 10 minus 5i plus 8 plus 6i. So just as a side note here, Zx in parallel with Zy I did this correctly, which I believe I did, came out to be 6.202 with an angle of 7.125 degrees ohms, which I have since stored in my calculator as X. And so now I get to be really lazy and do 50 angle 50 times X over X over 2 plus X. And I get 37.861 and some change. Angle 51.736 degrees, volts RMS, storing this in my calculator as Y. All right, so the complex power absorbed by impedance ZX is nothing more than the magnitude of the voltage drop across element X, or ZX, divided by the conjugate of impedance ZX. So that's going to look like 37.861 volts RMS squared divided by 10 plus J5. So the magnitude of what I have stored as Y squared divided by 10 plus 5I gives me 128.215 with an angle of negative 26.565 degrees, volt amperes in polar form. And converting this into rectangular form, we get 114.679 minus J 57.339 volt amperes. Which of those four numbers that I just wrote down is the average power? 114.679. Absolutely right. So the real part of the complex power, which is the bit that doesn't have a J in rectangular form, is our average power. So PX is 114.679 watts. We can find the complex power absorbed by impedance ZY using the exact same method. Oh, sorry, that should have been a squared there. So that's going to be Vx magnitude squared divided by ZY conjugate. We're putting Vx here because Vx is the same voltage as Vy. So once again, we're going to have 37.861 volts RMS squared. Zy was 8 plus J6, so Zy conjugate is 8 minus J6. So magnitude of what I have stored as Y squared divided by 8 minus 6I. I get 143.348 with an angle of 36.870 degrees. Volt amperes. In rectangular form, that comes out to be 114.679 plus J 86.009 volt amperes. And which of these numbers is the reactive power? 86.009. Yep. VAR. Our current IVS is 50 angle 50 degrees, volts RMS minus Vx divided by 2 ohms. So 50 angle 50 minus X. Comes out to be 22.825 with an angle of 55.304 degrees, amps RMS. And from this, the power factor at which our voltage source is supplying power is the cosine of 50 degrees. So that's the phase angle of our voltage minus 55.304 degrees which comes out to be 0.996. Is this power factor leading or lagging? Leading. So we've worked a couple of problems here with impedances specifically. Another type of problem that we will very frequently see is where we're provided information about a load with regard to either its average power or its apparent power that's drawn. So let's work another example problem here. So let's say that we have the following circuit. So here I have an impedance of 0.2 plus J 0.04 ohms. And this black box right here represents a load of an unknown impedance that draws 10 watts at a power factor of 0.9. Let me put it as PF is equal to 0.9 lagging. Then we have another impedance representing a portion of transmission line or something like that, where we have an impedance of 0.3 plus J 0.15 ohms. I'm going to have a second load here. Let's say that this one absorbs 15 volt amperes at a power factor of 0.85 lagging. And let's say that the magnitude of the voltage drop across this load 2 is 120 volts RMS. And I want us to determine the value of the capacitance C here such that the power factor of the voltage source is equal to 0.95 lagging after power factor correction. So this problem is kind of tying everything that we've talked about over the last couple of days together. So I want you guys to notice here that I explicitly did not tell you what that voltage Vs is. Okay. Ultimately, the only thing that we're going to need to use that value for is knowing what its magnitude is in our capacitance calculation, okay? So effectively, we're going to work this circuit from right to left in order to figure out what's going on, okay? So let's start by looking at load 2. So I'm going to put this 2 down here indicating that that's load 2, this 1 down here indicating that this is load 1. So let's find complex power absorbed by load 2 first. Anybody have any thoughts on how we might do that? If you took circuits 1 with me, I ask you to do this kind of stuff very often. So let me rephrase things, okay? What is our definition for power factor? We should have kind of 2 of them and they're equal to each other, right? So go back in your notes and tell me what mathematical relationships I introduced when we started talking about power factor. So the ratio of the average power, sorry, I need that thing to go away, to what? So apparent power, all right. And then my other relationship was power factor A. Yep. Okay. So 15 volt amperes, what does that represent? Average power or apparent power? Apparent power, because the units tell us that it's apparent power, right? So my complex power is going to be my apparent power with an angle of the inverse cosine of my power factor. Now, we are assuming a positive sign in front of that inverse cosine operation because our power factor is lagging. If our power factor were leading, we would have to include a negative sign in front of that inverse cosine because the inverse cosine operation on our calculator is always going to give us a positive angle. So just wanted to point that out. So this is going to look like 15 with an angle of the inverse cosine of 0.85. Which I get to be 15 angle 31.788 and some change degrees volt amperes. We're going to leave this as is. Okay. So let's call this guy right here ZW2 and this guy over here ZW1. Okay. If I wanted to find let me move this down so that we can do an intermediate step in a moment. The total complex power absorbed by that impedance, ZW2, I would need to know either the voltage drop across that load or that impedance or the current flowing through that impedance. Based on the information that we have been provided, the only thing I could figure out would be the current because I don't know what my source voltage is or anything really to the left there, right? So let's call this current, at least in magnitude, IW2, right? How would we find the magnitude of IW2? Elaborate, please.
Parent power divided by no. Parent power divided by DW2.
Okay. So I would argue, and I even drew it on the figure this way, that the current that's flowing through that 0.3 plus J 0.15 ohm impedance, which I'm calling ZW2, is the same current that's flowing through our load 2, right? Because the terminals on the right-hand side are open circuited. So I know the complex power that was absorbed by load 2. We just calculated that. I also know the magnitude of the voltage drop across load 2. It's 120 volts RMS. And actually, let me add something here. When we finally get around to the capacitor calculation, we're going to need a frequency, and I forgot about that until right now. So just adding it on there. So anyway, I would argue that the magnitude of the current IW2 is going to be the magnitude of complex power S2 divided by the magnitude of the L2. So effectively, since apparent power is effective voltage times effective current is nothing more than apparent power divided by effective voltage. Anybody have beef with that? So that gives us 15 volt amperes divided by 120 volts RMS comes out to be 1/8 of an amp RMS. Now that we know the magnitude of that current, the total complex power is just going to be absorbed by that impedance is going to be the magnitude of the current squared times the impedance. right? So 1/8 squared times 0.3 plus 0.15 I comes out to be 0.005. Actually, let's do it like this. 5.241. Angle 26.565 degrees. Millivoltamperes, which I'm storing as Y. And I stored this guy as X. All right. Total complex power, or excuse me, complex power absorbed by load one. How are we going to determine that? So it's similar to what we did for load two, except that we were given something in watts as opposed to something in voltamperes. So whenever I give you a power in watts, what does that mean? Average power. So you have average power and you have power factor. So I would argue that we could rearrange this relationship right here in order to find apparent power. And then we're going to find our power factor angle the exact same way that we did previously, inverse cosine of power factor, right? So this should be nothing more than P1 divided by power factor 1 with an angle of the inverse cosine of the power factor of load 1. Putting numbers in, this is going to look like 10 over 0.9 with an inverse angle of inverse cosine of 0.9. Comes out to be 11.111 with an angle of positive 25.842 degrees. Volt ampere. And I've stored this in my calculator as Z. So here's where things are going to start getting a little difficult. Okay. So I'm working my way through this circuit from left to right because I know that if I can find the complex power absorbed by load one, complex power absorbed by load two, complex power absorbed by impedance ZW2, and the complex power absorbed by impedance ZW1, if I add all of those together, I will get the complex power that is supplied by my voltage source, which will let me know what's going on with the voltage source, right? Like from that, I can calculate power factors and all those kind of good things, okay? We have calculated the complex power absorbed by load 1, complex power absorbed by load 2, and the complex power absorbed by impedance ZW2. Finding the complex power absorbed by impedance ZW1 is more difficult because we weren't given any information about the current that flows through load 1 or the voltage drop across load 1, right? So we are effectively going to have to make an assumption here, okay? And so what I am going to assume is that the angle on this voltage was 0 degrees. So let's talk about what that's going to mean. Effectively, we are treating that voltage VL2 as if it were a reference, okay? Or at least the phase angle there is a reference. Because we're ultimately only concerned about getting a magnitude of a voltage in order to calculate that capacitance, this is going to work out for us fine because the phase angles is completely inconsequential. So we could assume literally any phase angle for our voltage and everything would come out to be okay. 0 is just something that's easy and convenient. So if we assume let me put a voltage here. Let's do it in orange. Let's call it VL1. If we can figure out what this voltage VL1 is, actually, let me make it more obvious that it's the voltage drop across this load. If we can figure out what that voltage VL1 is, we can very easily find the current flowing through that load, and then use Kirchhoff's current law to find the current that's flowing through that impedance 0 plus 2 plus J 0.04 ohms, the impedance ZW1, right? So how might we find that voltage VL1? So I'm not looking for anything specific. We'll sort that out in a moment, but like, what information do we have kind of thing? Like what steps might you take? Henry, what are you thinking? I think you're on the right track here. Yeah, so what I would do is use a combination of Ohm's law and Kirchhoff's voltage law, okay? So effectively what I'm thinking is that voltage drop VL1 is just going to be the sum of the voltage drop across that impedance ZW2 plus the voltage drop across that load VL2, right? So VL1 is whatever IW2 is times ZW2. Remember, right now we only know the impedance of IW2, but we'll sort that out in a moment. Plus VL1. So I'm going to put a note here. Assuming the angle of VL2 is equal to 0 degrees, then our current would be our complex power 2 divided by VL1 conjugate times ZW2 plus VL1. So just to be very explicit about where this stuff is coming from, I'm going to write it in blue. We know, generally speaking, that S is equal to V times I conjugate. So I conjugate is then S over V. And to get rid of the conjugate on the left-hand side of the equal sign, we have to conjugate the right-hand side. So that's all that I did in this step, right? So putting numbers in, we would have 15 angle negative 31.788 degrees volt amperes. The negative sign there is because when you conjugate a polar form complex number, you change the sign on the angle. VL1 is simply 120 angle 0, so the conjugate of VL1 is also 120 degrees angle 0. I'm going to put negative 0 degrees here, just so that we're aware we're conjugating both the numerator and the denominator. This gets multiplied by the impedance ZW2, which is 0.3 plus J 0.15. And then to this we add 120 angle 0 degrees. Let me put my volts here. All right, so throwing this into my calculator. I got 120.042 angle negative 0.002 degrees volts RMS. I'm going to store that as D. So this shouldn't be a hugely surprising result. We know that the current that's flowing through that impedance of ZW2 was very small. It was only 1/8 of an amp. The impedance itself was small, 0.3 plus J0, 1.5 ohms. So the voltage drop across it isn't particularly large. Add that to 120 and we get something very close to 120. But now we have a more accurate representation. Okay. All right, so let's put a label on this current right here. Let's call this IW1. So how would we find that current IW1? So I would argue that current IW1 is just the sum of the current flowing down into load 1, which we're just going to express in terms of the voltage drop across load 1 and the complex power absorbed by load 1, plus that current IW2, right? So that's going to look like S1 over VL1 conjugate. So that's the current flowing down through load 1 plus S2 over 120 angle 0 conjugate. That's just me adding those two currents together, right? So that would look like 11.111 angle negative 25.842 degrees. Divided by 120.042 with an angle of positive 0.002 degrees volts plus 15 angle negative 31.788 degrees volt amperes divided by 120 angle negative 0 degrees volts. So let me see what I stored this in my calculator. So for me, that's going to look like the conjugate of Z divided by the conjugate of D plus conjugate of X divided by 120. We get 0.217 angle negative 29.260 degrees. Amps RMS, and I'm going to store this as A. All right, so from here, actually, let's stop here because we have less than a minute of class and we've got more steps to do. So we'll finish this problem up at the beginning of class on Friday before we get into filter circuits. For what it's worth, this is literally like the hardest thing I could ask you guys to do. Adding in that extra impedance between load 1 and load 2 is what made this difficult. So anyway. All right, thank you guys for putting up with me. I'll see you on Friday.